Hi, everyone. My name is Isil Dillig. I am the president of a startup called Veridise, and I'm also a computer science professor at the University of Texas at Austin. And today I'd like to tell you about a research area called formal methods, and in particular how this field of formal methods can help us improve blockchain security. So first of all, let me start by stating the obvious, which is that bugs in blockchain software, as we all know, tend to be extremely costly, right? And when I talk about blockchain software, of course, this includes DeFi applications and smart contracts and Web3 applications, but it also includes the underlying blockchain implementation, for example, consensus protocols, as well as zero-knowledge proof circuits. And if you have a logical bug or a security vulnerability in any of those layers, they can have catastrophic consequences if and when they're exploited. So let me give you a few examples to illustrate the impact of these bugs. So as an example, there was recently a flash loan vulnerability in a smart contract in the Beanstalk DeFi protocol. And when that flash loan vulnerability was exploited, that resulted in a loss of $182 million worth of cryptocurrency. Now, you can also have serious security vulnerabilities in the underlying blockchain implementation. As an example, there was recently a denial of service vulnerability in the consensus protocol of Solana. And when that vulnerability was exploited, that resulted in network outage and caused the Solana prices to plunge and lose more than 12% of their value overnight. And last but not least, you can also have serious security vulnerabilities in zero-knowledge proofs. And to illustrate that, there was actually a bug in an arithmetic circuit implementing a ZK snark in the Zcash protocol. And if that vulnerability had been exploited, this would have allowed attackers to create a very large number of fake Zcash coins, which is obviously problematic. Now you're probably thinking, well, that's pretty depressing, but it's something I see in the news every day. Well, the good news is that what I'm here to tell you is that these kinds of bugs and security vulnerabilities are actually maybe not as inevitable as that they might seem. And in fact, this research area called formal methods can help us eradicate these bugs. So in the remainder of the talk, I want to tell you, give you an overview of what formal methods is all about and how we can leverage it to improve blockchain security. So for those of you who may not have heard the term, basically formal methods refers to a set of mathematically rigorous techniques that can be used to automatically find bugs in software and also to automatically construct proofs about program correctness. Now, when you hear the term formal methods, you shouldn't think of it as one specific technique, but you should rather think of it as basically a spectrum of different techniques that have different trade-offs. And these techniques include things like automated testing, static analysis, and formal verification. And generally speaking, the further to the right you go on the spectrum, the stronger the guarantees that you get. But as we all know, there's typically no free lunch. So if you want to get very strong guarantees about your software, you also need to be willing to invest more human effort into the process. Now, at a very high level, you can classify formal methods techniques as either being dynamic or static, depending on whether they execute your program or not. So in particular, dynamic techniques basically generate, in a systematic way, a set of interesting inputs, and they execute the program on those inputs, and they monitor what happens and see if some key property is violated or not. On the other hand, static techniques don't actually run the program. They literally stare at the source code of your program, and they try to reason about all executions at the same time by performing some kind of approximations, as we will see shortly. And as you can imagine, static and dynamic techniques have complementary strengths. They have different pros and cons. So specifically, the big advantage of static analysis is that they can be used to reason about all executions of the program, possibly infinite space of executions. And in addition to being useful as a bug-finding technique, they can also be used to construct proofs of program correctness precisely because of their ability to reason about all executions at the same time. In contrast, dynamic techniques rely on executing a fixed set of inputs, so therefore they're primarily useful as a bug-finding tool, but you cannot give guarantees using dynamic techniques. On the other hand, the big advantage of dynamic analysis over static analysis is that they don't report false positives. When a dynamic analysis tool says there is a bug or a security vulnerability in your code, you can rest assured that there is actually a problem. Whereas with static analysis, as I mentioned earlier, they rely on performing some sort of approximate reasoning, so they may, as a result, report false positives. So when they report a bug, that may or may not correspond to an actual bug in the program. So now, whenever I talk about static and dynamic analysis, most people have the reaction, well, dynamic analysis, that makes sense. It sort of sounds like automated testing. But what the heck is static analysis, right? Like, what does it mean to reason about all executions? Everyone has this reaction that it sounds really mysterious. So to kind of demystify static analysis, let's just take a look and understand how it works at a very high level. So basically, the key idea underlying static analysis is essentially to emulate all possible executions of the program by symbolically executing the different paths. Okay, so what do I mean by that? So basically, the idea is that whenever you have a branching point in the code, whenever you could take this branch or that branch, you conservatively assume that either path could be taken. You symbolically execute both of those branches. You collect some information. And when there is a merge point in the code, you summarize, you combine the information that you gathered along the different branches. So very simple example here. Let's say in this code snippet, you're assigning x to either 1 or -1, depending on whether flag is true. So basically, a static analysis tool would separately analyze one branch, and then it would analyze the other branch, and then it would combine this information. So for instance, in this case, it might say that x is some value in the range -1 to 1, even though we don't know exactly what it is. And now you see what I mean by static analysis introducing approximations, and you can probably see why you potentially get false positives when you do static analysis. Okay, so hopefully that gives everyone some intuition about static analysis. But you're probably asking, what can you actually prove using static analysis? Well, the answer to that question is it depends, and in particular, it depends on how much effort you as a user are willing to put into the verification. And in particular, if you want to get strong guarantees, you as a user need to write something which is called a formal specification. And in a nutshell, a formal specification is a mathematically precise description of the intended correct behavior of the program. And the key thing here is that a formal specification needs to be mathematically precise. It needs to be something that has very precise semantics. So therefore, formal specifications are typically expressed in some sort of formal logic. For example, it can be first-order logic, or it can be some sort of temporal logic. So as a quick example, let's say you have a DeFi protocol that's implementing an auction. And here, one of the properties that you might care about an auction is if the auction closes and I'm not the winner of the auction, I should naturally expect to get my bid back, right? So if you want to get strong guarantees using static analysis, you need to formally express this property. And here on this slide, you see a formalization of this property in a logic called linear temporal logic. So basically, this box over here means always, this diamond means eventually, and basically it's saying if the auction has closed and I'm not the winner of the auction, then eventually I'm going to be sent exactly the amount of money that I initially bid. Okay, so that's a formal specification of this intuitive English property. Now, the cool thing about writing formal specifications is that once you take the trouble of writing a formal specification, we can use automated or at least semi-automated tools to check whether the implementation adheres to the specification or not. And again, the nice thing here is that assuming that you've written a specification that's both correct and complete, and that's a big if there, that's not trivial, you can use formal verification tools to find any logical bug in the program or prove the absence of any logical bug, which is a very, very strong and very nice guarantee. But of course, in many cases, it's not that easy to write these formal specifications. So if you don't want to write these specifications, you can still apply static analysis. For example, you can use techniques like abstract interpretation to look for known types of bugs in your software. For example, you can show that there are no arithmetic overflows, or you can use a static analyzer to look for reentrancy or flash loan vulnerabilities and so on. But of course, you don't get as strong guarantees because we're looking for specific classes of bugs, right? So in the case where you verify something, you're saying I verified under certain assumptions that we don't have this class of bugs in the code. So hopefully that gives you some idea about kind of the landscape of different formal verification techniques. But taking a step back, what I want to emphasize here is that, as you can see, there are many different techniques that we can throw at the problem, and they all have different trade-offs. They have complementary strengths. They each have their own pros and cons. And in my opinion, as a formal methods researcher for many years, I think it would be fair to say that there isn't one formal methods technique that's universally the best, that's going to be the one-size-fits-all solution that's going to cater to every one of your needs. So this brings me to the philosophy of our startup, Veridise, which is basically to embrace the fact that different techniques have complementary strengths, they have different pros and cons. So rather than trying to apply the same hammer to all the different nails out there, what we try to do is we try to find the right tool to attack the right problem and use different tools in ways that are complementary. And based on that philosophy, we develop and utilize a wide range of formal methods tools with the goal of being able to uncover defects, not just in Web3 applications or smart contracts, but with the goal of addressing problems in all layers of the blockchain ecosystem, ranging from the blockchain implementations to problems with zero-knowledge proofs, as well as DeFi and Web3 applications. And based on that philosophy, we've been building a range of formal methods software that can be used to mostly automatically analyze blockchain applications. So just to give you some idea, we have a tool called Vanguard, and some version of this is actually available as open source. And Vanguard performs static analysis to look for common vulnerabilities in blockchain applications. And what kind of vulnerability we'll look for depends on what layer you're targeting. We also have automated testing tools based on fuzzing and property-directed checking. And these can look for both common vulnerabilities as well as logical bugs, assuming that you give us some sort of specification. And we also have a deductive verification tool that takes, in addition to your source code, some specification written in our specification language called V, and it checks whether your implementation adheres to the specification. And last but not least, we've also been building this tool called URAS that basically helps us deal with the shortcomings of static analysis and verification tools. So as I mentioned, one of the shortcomings of static analysis is that they can report false alarms. So when it reports a report, you don't know whether that is a real bug or not. So we've built this tool called URAS. In the case where one of our tools reports a vulnerability, it tries to automatically construct an exploit that shows how that vulnerability can be taken advantage of. And another thing I want to point out about kind of our philosophy here is we recognize that there are many different languages out there, Solidity, Rust, and many different blockchains, and like people want to use many of them or a combination of them. So we try to build tools that can be applied to multiple languages by doing our analyses at an intermediate representation. And a lot of our tools are also applicable to multiple blockchains, not just Ethereum. And across all of these tools, we can use them to uncover both logical bugs and known types of vulnerabilities. So based on all this tooling that we've built, during our security audits, we've been able to uncover many zero-day vulnerabilities with the help of all these tools, which would have been very hard to do if we didn't have these tools. So for example, we've been auditing DeFi applications, and we found a number of issues, obviously like things like flash loan and reentrancy vulnerabilities, but also things like access control problems and locked funds. We've also done security audits for the blockchain implementations themselves. For example, we found serious denial of service vulnerabilities in the underlying consensus protocols. And last but not least, we're also in the process of building a bunch of tooling for zero-knowledge proof circuits, specifically targeting circum circuits and Cairo, and some of these tools can also find soundness bugs in zero-knowledge proofs. So basically, the point that I want to make, the more broader point, is that the motto here is that tools and humans are much better together in the sense that formal methods tools can really help security auditors perform their audits much more effectively and much more consistently because they can help humans to realize edge cases that they normally wouldn't think about. So they're a really good way to augment human intelligence. So in addition to performing security audits that are heavily assisted by formal methods tools, we are also in the process of starting what I call verification as a service. And the idea here is that our clients will be able to upload their source code into our servers and use our formal methods tools to automatically analyze the code and get results in real time and perform continuous integration. So basically, as a concluding thought, so the one thing I really would like everyone to take away from this talk is that tools and humans are much better together, and formal methods can make auditing much more consistent, scalable, and cost-effective because they can help uncover security vulnerabilities in a more automated fashion than just humans alone can. So that's all I have. Thank you very much. If you have any questions, I'm happy to take them.
Hi there. I have two quick questions.
Sure.
Firstly, formal methods has been around for a very long time, and I've been doing security 20+ years. I haven't really seen that amount of traction for formal methods other than in very specific edge cases, which is mostly military certified systems.
Haven't we seen?
I haven't seen formally verified systems. For the last 20+ years, Red Book, if you look at it, it's a specification for formally verified techniques. We haven't seen adoption in the space, as in like in security, general security, not even blockchain, right? Number one, it implies A, scarcity of skills, B, difficulty. The logic that you write down and the logic that you build, that is a key problem, right? Like if the two are inconsistent, there is zero value in actually having formal methods. Second thing is I want to understand how you would provide soundness proof for Circom, because I deploy something on Circom, I use .16, so I'd be curious to know how you do that.
Okay, so first question, I absolutely agree with you that, and that's why I said tools are not a substitute for humans, because in order to formally verify anything, you need to write formal specifications, and if you don't have formal specifications, or if they're incorrect or they're incomplete, then the formal verification guarantees that you get are going to be only as good as your specifications, right? So regarding your question about Circom, that would be probably like a topic for an entirely different talk. I could just talk about it like for, so we have, for more challenging Circom proofs, we have cock-based techniques for proving their correctness, and for not the libraries, but the stuff that build on top of those libraries, we have more automated ways of proving them, but as I said, that's like that would be an entirely different talk in its own right.
Hi, I have a short question. How long does it take to have a formal verification, let's say, from Veridise?
Oh, that totally depends on the complexity of what you're trying to analyze and the complexity of your specification. And generally speaking, when I showed that spectrum, the lighter weight techniques tend to take less time, whereas like the more strong guarantees you want to give, the longer. Sorry? So, for example, if you use a deductive verification tool and you're willing to write like these pre and post conditions and method contracts, then you can make verification modular. So that would basically like mitigate some of the, basically anytime you can make something modular, then you can scale pretty much linearly with respect to the number of methods that you have. No, we're talking about like, you know, minutes or tens of minutes, right?
Yeah, I was wondering, you said that all of these 4 tools are all blockchain agnostic and language agnostic. So I'm wondering how you achieve that. Does that mean that you...
That's a great question, yeah. So I tried to hint at it, but the way we do it, I shouldn't say they're completely language and blockchain agnostic. So what we do is we build our tools at the intermediate representation level, at the LLVM bitcode level. And basically, we instrument when we do that translation from source code to the intermediate representation, we instrument it with blockchain-specific assumptions. So that's so in order to support a new language and a new blockchain, you still need to, you know, modify that translation step or add that translation step. But once you do that, of course, that's much easier than building a tool from scratch. That's what I mean by language and blockchain agnostic.